Hi, in this video we will derive the equation for moment of inertia of semicircle. Okay, so I have considered a semicircle uh, of radius r, capital R. Let me mark the centroid first. G is the centroid of semicircle. So I am writing centroidal x-axis and centroidal y-axis, about which we have to derive the equation for moment of inertia. Correct? This is centroidal x-axis and centroidal y-axis. Okay, let me call these points as points A and B. Okay, now we have to obtain the expression for Ixx and the Iyy. Okay, now moment of inertia about the diametric axis AB will be equal to, from figure, moment of inertia of semicircle about AB is equal to IAB is equal to, now I will complete this semicircle. Okay, it is IAB is equal to half of moment of inertia of the circle, or moment of inertia of circle divided by 2. Okay, moment of inertia about axis AB is equal to half of moment of inertia of the circle. We know the formula for moment of inertia of the circle. Correct? It is what? Pi r raised to 4 by 4. Okay, now IAB is equal to pi r raised to 4 by 4 is moment of inertia of circle divided by 2. Therefore IAB is equal to pi r raised to 4 by 8. Okay, now we got moment of inertia of semicircle about its diameter AB, IAB, but we want moment of inertia about centroidal axis. Okay, we want moment of inertia about x-axis and we want moment of inertia about y-axis, Ixx and Iyy. To obtain or to derive the equation for Ixx, what we have to do is we have to utilize the parallel axis theorem. Okay, we have to utilize the parallel axis theorem. Therefore, from parallel axis theorem, okay, so with respect to semicircle, I will define the parallel axis theorem. If Ixx is the moment of inertia of this semicircle passing through the centroid, then moment of inertia of the semicircle about axis AB, which is parallel to x-axis, is given by Ixx plus A into y bar square. Okay, now we will use this equation and we will obtain the expression for Ixx. Therefore Ixx is equal to IAB plus A into, sorry, IAB is equal to Ixx plus A into y bar square. IAB is equal to Ixx plus A into y bar square. Okay, Therefore Ixx is equal to IAB minus A into y bar square. IAB is what? Pi r raised to 4 by 8, but IAB is equal to pi r raised to 4 by 8. And what is capital A? Capital A is nothing but area of the semicircle, that is pi r square by 2, half of the area of the circle. And what is the formula for y bar for semicircle? For semicircle, y bar is equal to 4r by 3 pi. From centroid of the plane figure chapter, we know this equation, correct? Y bar is equal to 4r by 3 pi, and y bar is equal to 4r by 3 pi. Now what you have to do? You have to substitute the values of IAB, area, and y bar in this equation 1. Okay, therefore equation 1 becomes Ixx is equal to IAB pi r raised to 4 by 8, pi r raised to 4 by 8 minus A into y bar square. A is pi r square by 2, y bar square means 4r by 3 pi whole square. Therefore pi r raised to 4 by 8 minus, so we have to simplify this equation, pi r square divided by 2, 4r whole square is there, it will be 16 r square divided by 9 pi square, correct? 16 r square by 9 pi square. Pi gets cancelled, therefore it is pi r raised to 4 by 8 minus 16 r to the power of 4 divided by 18 pi. What we will do is we will take this r to the power of 4 common. In the bracket, what we will get? It is pi by 8 minus 16 divided by 18 pi. Now we will find the value of this bracket term. Okay, pi by 8 minus 16 divided by 18 pi. Okay, so it is how much? 0.109 0.1097 r to the power of 4 into 0.1097. We can round it off this value as 0.11. Okay, because 97 is there, no? So we can write this equation as 0.11 r to the power of 4, which is the formula for moment of inertia about x-axis. Okay, so for semicircle, moment of inertia about this x-axis, which is parallel to the diameter, is 0.11 r to the power of 4. Okay, now we got the expression for Ixx, and moment of inertia about y-axis is equal to it is directly half of moment of inertia of the circle. Okay, half of or moment of inertia of circle divided by 2. So we know that equation already. Moment of inertia of circle divided by 2 is, it is pi r raised to 4 by 8. Therefore moment of inertia about y is equal to pi r raised to 4 by 8. So this is the final expression for moment of inertia about y-axis. See, for Iyy, no need to use the parallax theorem, because why? Because see centroidal y-axis for the semicircle and centroidal y-axis for the whole circle, both are same, therefore Iyy is equal to half of moment of inertia of circle directly. But when it comes to the x-axis, centroidal x-axis for the semicircle and centroidal x-axis for the whole circle, both are different, therefore we have utilized parallel axis theorem. Okay, we got it as 0.11 r to the power of 4. Okay, but with respect to y-axis, centroidal y-axis for the semicircle and centroidal y-axis for the whole circle, both are same only. No need to use the parallel axis theorem. It is directly half of moment of inertia of the circle, that is pi r raised to 4 by 8. Okay, so for semicircle you need to remember the formula in general way, means depending upon the orientation the formula will change. See, if the orientation of semicircle is like this, okay, moment of inertia about an axis which is parallel to the diametric axis Ixx is always 0.11 r to the power of 4. And if I draw the y-axis, so in this case y-axis is the axis which is perpendicular to the diameter. Iyy is equal to pi r raised to 4 by 8. If I change the orientation like this, if I change the orientation of the semicircle like this, so here in this case Ixx becomes the axis which is perpendicular to the diameter, and Iyy becomes an axis which is parallel to the diameter. In this case the formula will be reversed. Ixx becomes pi r raised to 4 by 8, and Iyy becomes 0.11 r to the power of 4. So depending upon the orientation the formula will change. Okay, so this concept is required to solve the problems, that's why I explained. Okay, so don't have the fixed formula in your mind. Okay, that Ixx is equal to 0.11 r to the power of 4 and Iyy is equal to pi r raised to 4 by 8. Actually this formula will vary according to the orientation of the semicircle. Okay, so this completes the derivation of the moment of inertia of the semicircle. Okay, thank you.